Okay, so we're going to look at the derivative as talking about the rate of change. I'm going to leave this up here. I might scroll back to it as we work out. And so if we want to think about instantaneous change, or how a function is changing at an instant, what we can say is at a given point on the function, so x sub naught will be a given point, then in this limit that we've been looking at, as f of x approaches h minus f of x sub naught all over h is telling me the rate of change, right? Because we're getting a change in the y over the change in the x, and so this is slope. It is also the rate of change, right? The ratio y is changing with x, but in an instant, an instantaneous rate of change. So the example your book does is, if we look at a circle, it's a little bit closer than I want, but we'll say that we're at the internal circle here, and we're wondering how the circle is changing if the radius is growing or shrinking. And in this case, we're going to grow outwards. And so let me make this a bigger set of circles here. So we have some given circle, and then we're going to have some other circle. Let me see if I can get it bigger than that. And we are at the point of this inner diameter, and we want to know if the diameter changes, or some delta d change in diameter, what's happening to the overall area of the circle? What is the changing delta in A? How is the area changing? And so we can use the derivative to talk about this. So if we look at the area of a circle being pi divided by 4 times d squared, and we're going to ask ourselves, if we're going to take the derivative of the area with respect to diameter, what we're asking for is the derivative with respect to diameter of the right-hand side. And so the derivative with respect to diameter, or the change in area with the change in diameter, is equal to, well, I'll bring my, we'll bring this out front. So it's 2 divided by 4, or pi over 2 times the diameter. So whatever diameter we are at, the rate of change in area is going to be related to this. So if the diameter is 10 meters, then in any change, the change of area with respect would be 2 and so it would be changing 5 pi meters squared per meter, right? Because this is a change in meters squared, this is a change in meters. And so for every meter change in diameter, we're going to get a 5 pi change in the area. So this is the idea of an instantaneous change, that we can have some ratio that represents what's going to happen if we change parameters at a given point within the feature. Let's continue. The book's going to look at displacement, where they're going to say your positional displaced on a curve is going to be S. I think I've warned you, try to warn a lot of my students, mathematicians like S's for position on a curve because it looks like a curve. Where physicists will say this is your X displacement value, your positional X displacement. And so what we can say is that or S is position, X is your position on some curve, on some number line, on some axis. You set up a relative origin point and you go from there. So displacement is our change in S. If I have a particle and I'm at position, some initial position and some final position, my displacement is the final minus the initial, and it will have directional implications. It will tell in which direction I change, because x final minus x initial, if it's positive, the change is in this direction. If it's negative, the change is in this direction. So we can think of the displacement as the function in time plus whatever time period has changed minus where we started initially. Right? Because displacement in physical objects don't happen without time changing. You don't move without time. So we can say the average velocity is your displacement over the time traveled, which is delta S over delta T. And our average begins to start looking very much like our difference quotient that we've been using. And so we can change the average velocity to the instantaneous velocity by taking the limit, by making delta t approach 0. So we're literally trying to find an instant. And we've talked about this definition as we've been building these things. The book cycles back to it in different regions. Now, an instantaneous velocity is directional. And a good example of a instantaneous velocity of 0, but where something has actually had some distance traveled, but not a displacement. So you think of someone running around a track. If they start here and run all the way around and get back to here, their initial position and final position are the same. They have not displaced at all. They might have covered a distance, which is a non-directional amount of motion, but they did their average velocity was 0. To deal with the positional displacement versus distance, we have a concept called speed, which is the absolute value of the velocity, or ds over dt. And I have been trying to say this continues. So we can have acceleration, which is a change in velocity with respect to time. So the acceleration of an object is the change of its velocities over time, which is equivalent to the second derivative of its position with respect to time. And then in the book goes on to talk about the jerk, which is the change in accelerations. And that's a change in acceleration with respect to time, which is the second derivative of velocity with respect to time, which is the third derivative of position with respect to time. A good example of this is they show that free fall is jerkless. So we can monitor the position of an object under gravity as being 1/2 the gravitational constant times t squared. So if I were to take an object and I were to drop it vertically, then as it fell, its position grows with powers of t squared. And so it has this increasing or squaring of the distances that it travels on each time segment. Well, to see this, we'll work out what is happening. So if we take the derivative of something in free fall, we'll see that its velocity, so we'll take the derivative, so we'll multiply the 2 out front and bring the power down. So, so the velocity of an object at a given time is gt. And the acceleration is the derivative of velocity. So we'll take the derivative of gt and we get g. And this is another subtle way of saying, hey, look, acceleration is constant in free fall, and the constant is this gravitational constant that we've been using. And so that they're linked. And, well, if we look at the jerk then, so we take the derivative of acceleration with respect to time, which is the derivative of a constant, that's 0. So the jerk of an object in free fall is 0. It does not experience jerky motion because the acceleration itself is a constant. Let's look at how these rates of change come together. I'm going to stop this here, and this has gotten us kind of into the examples in Chapter 3, Section 4, and the ideas. I know I talk about these ideas when we were defining the derivatives, so that we would have the nomenclature, and the book takes a pause and introduces these here. And so give me a second. I will start up with a second video in a second.